Welcome back to the final lecture in our course on symplectic geometry. We're going to finish up the course by looking at a very special class of symplectic manifolds called Kähler manifolds. And I'm going to sketch the relationship between the geometry of Kähler manifolds and that of quantum mechanics. So that's the final objective for this course, that you can in some sense see this lecture as really the invitation to a whole other line of research that continues to this day. Before I talk about quantum mechanics, I have to tell you about what these Kähler manifolds are. Well, we've actually are already familiar with them because they are manifolds that are simultaneously symplectic and complex at the same time in a way that's compatible with each other. So to get actually to the definition, however, which is the one that will be useful in practice, we have to go through a little bit of formalism still concerning differential forms on complex manifolds. And the first piece of formalism we have to deal with today is that of the exterior derivative for complex manifolds and almost complex manifolds, and some of the internal substructure of the exterior derivative operator. So last time we heard about these things called R, S forms. So let's suppose we have an R, S form on a complex manifold M. Well, we can compute its exterior derivative. If we think of our complex manifold M just as a real manifold with some extra structure on it, you can, as before, compute the exterior derivative of that form, and that should give you, if we have the complex dimension of our manifold is n, and R plus S is n, then we should have a 2n plus 1 dimensional form, real form, coming out of this thing. Now, if you choose to write this out in some chart with complex coordinates z, then we can write the exterior derivative out in terms of real and imaginary components as before. Or we can write it out in terms of our complex variables, z and z bar. And then it's a little exercise that when you do that, that the result has a particular form, which is very useful. So if we express our RS form in these complex coordinates z bar, then you know you can write any RS form as in coordinates as the wedge product of some dz's or r dz's and s dz bars. And then the exterior derivative, whatever is in the brackets here, it's got to be that thing that you wedge on when you apply the d operator. And it just so happens that when you write it out in terms of z and z bar coordinates, that it has this particular form there. So this is a combination. What do you see here? Well, we see we get two differential forms. We get an R plus 1 S form. Oops. And an RS plus 1 form when you do that exterior derivative. Kind of interesting. Sort of see that the exterior derivative on a complex manifold itself can be kind of written as a real and imaginary, as a holomorphic and an anti-holomorphic part. If you like, this first term here is like a holomorphic exterior derivative, and the second thing here is like an anti-holomorphic exterior derivative. And we're going to capture that by introducing two new linear operators, exterior derivative-like operators. We're going to express our exterior derivative as a combination of two operators, delta and delta bar, where delta takes an R plus S form, R comma S form to an R plus 1 S form. Delta bar does the same, but on the anti-holomorphic part. And we're going to define these operators just by capturing this decomposition here. So I'll just do it by example, but already the definition is fairly apparent in that formula there. So if in components we have a 2 form, for example, a 1 plus 1, a 1 comma 1 form, then we do define delta to be this operator, delta bar to be the other component. Started writing components upstairs, but just to be consistent with the rest of the text, I'll leave the components downstairs. At the moment, there's no particular meaning to upstairs or downstairs, but I don't want to be flipping between these two notations. So it's something you can do, right? We can separate out the holomorphic action, if you like, of D and the anti-holomorphic of action to introduce these operators here, delta and delta bar. And I've defined them by example, but I think you can see how to generalize this. And these operators have a name. They're called Dolbeau operators. just as it's useful to express things in terms of z's and complex conjugates of z's in complex analysis, it's useful to express things in terms, exterior derivatives in terms of deltas and delta bars. And as we'll see, whether or not something vanishes under the action of delta bar will have a important consequence for whether or not that thing is holomorphic or not. Now, this is, so far this looks very specific to complex manifolds where we have this local chart in terms of complex numbers or Cartesian product of n complex numbers. But it turns out you can actually define these operators for almost complex manifolds as well. I mean, you might guess that that's the case because everything here looks completely local, right? We don't have to make reference to the global topology of the manifold in order to define these operators. So let's extend them, and to do that we have to define a projection operator, pi r comma s, which takes a K-form to the subspace of R comma S forms. So this all makes sense on almost complex manifolds. I think I mean a Q form here. So we know that we can decompose, we saw this at the end of the last lecture, right? We can decompose the linear space of Q forms on an almost complex manifold into a direct sum of R comma S forms. So we define that projection operator there. It's just a standard projection on a vector space. And then define delta and delta bar in terms of the exterior derivative followed by a projection. That'll end up giving us something that's a natural analog of these operators for almost complex manifolds. So delta will be equivalent to first doing an exterior derivative and then projecting out on R plus 1, oops, and delta bar is the operator you get when you first do an exterior derivative and then project onto the RS plus 1 space. You can define these operators. Right? And you'll see that these definitions agree, at least for complex manifolds. So the exterior derivatives got many nice properties that were very useful in, for example, improving Stokes' theorem or defining cohomology theories. And one of the most vitally important properties of the exterior derivative is that if you do it twice, you get nothing. So that turned out to be the fundamental building block of many, many results in differential geometry. And there is a holomorphic and anti-holomorphic analog of these statements, or capture them now. I mean, they're not particularly difficult to prove because you just make reference to the original property that d squared is 0. Oh, before I continue, it's absolutely unclear from this definition if the exterior derivative is the sum of delta and delta bar. In fact, the property that delta plus delta bar is equal to d, which is just true in the complex manifold case per definition, that property will turn out to characterize to a large extent whether a manifold is complex manifold or not, or just almost complex. We'll see that soon. All right, let's capture some straightforward stuff about these Dolbeault operators for complex manifolds. I mean, ultimately, our interest doesn't really lie in almost complex manifolds. Our interest will lie in complex manifolds in this course. And those are a bit more special. So we have some Q form on a complex manifold, a complexified one, and we have some R form, or P form, make it a P form. Yeah. I forgot to be totally consistent with my complexifications. Then these delta operators, these Dolbeault operators, have a whole bunch of properties. None of them are particularly difficult to prove. Okay, the first really is just the manifestation of d squared is 0. The second one tells us that the delta operator is a real operator, not a real operator, that we can relate them by complex conjugation. The third one tells us that they obey Leibniz-like properties, so they are like exterior derivatives. And the fourth one says the same for delta bar. So they behave separately like exterior derivative operators. And in terms of these Dolbeault operators, we can now capture a notion of holomorphicity for forms, right? So it's fairly clear what a holomorphic function is. A function is a zero form, right? So a holomorphic function is something that only depends on z and not z bar. So that's for zero forms, that's the definition. What could it be for R plus S forms? Well, it doesn't make sense, really, for anything except R forms, R comma 0 forms. But there we can come up with a reasonable definition of what what holomorphic means. So suppose we have ourselves a complex manifold and we have our friendly r, 0 form. So that means it only has holomorphic terms when you expand it in terms of wedge products of coordinates. Now you might think, okay, that's a reasonable definition for what is a holomorphic form. Well, it's not, because the coefficients could still depend on z and z bar. So we have to come up with a notion of what holomorphic means here, and the natural one to write down is that delta bar of omega is 0. So if there's no dependence on z bars, then we can say that omega is holomorphic. All right, so we could say lots more about the geometry and topology of complex manifolds. There's easily a whole course in exploring the delta and delta bar operators, exploring the cohomology theories that you can build with them, exploring integration on complex manifolds. It's a massive subject. There's hundreds of pages of books devoted to this topic. We're not going to look at that theory so much. We're going to look at a special class of complex manifolds and largely use only a couple of simple properties of these operators. That's a shame, but we only have a finite amount of time to do things. And to transition to the special subclass of manifolds, I'm going to quote a very important result in symplectic geometry and more complex geometry. And this result captures the obstructions that stop an almost complex manifold from being a complex manifold. So it's sort of a natural question. If something's locally complex, like it's an almost complex manifold, what's really stopping it from being a complex manifold? And we're going to capture those obstructions here in a well-known, or not particularly well-known, but a central theorem in this topic. So suppose we have an almost complex manifold. We're going to define a special tensor, the Nierenhaus tensor, Nierenhaus. This will turn out to play an important role in whether or not an almost complex manifold is complex or not. Nierenhaus. I'm not sure how you would pronounce that, but so it's something local. Is it a tensor? Well, that's an exercise. At the moment, it eats two tangent vectors, and gives you back a tangent vector. That's all we can infer from what's written there. Whether or not this thing is a tensor requires a little proof. It's a good exercise. And just to remind you of the notation, this is the Lie bracket. So the exercise here is show that n is a tensor, meaning a multilinear function on Tm, tensor Tm, tensor Tm star. So when you've got an almost complex manifold, I mean, at least locally it looks complex, really locally on tangent space. We've seen that. And so what stops it from being complex is somehow if you extend this local complexness to the whole manifold. That's what's the obstruction here, right? As you try and consistently cover the manifold in little coordinate charts that you need that always when there's overlapping coordinate charts that the holomorphic bits go to holomorphic bits and the anti-holomorphic bits go to anti-holomorphic bits. And you see that there is somehow a global obstruction there. You know, it could be that you could patch things together locally for a bit and that very, very, very far away things might get inconsistent. You know, patching, and somehow you come around the manifold and you see that the way you've analytically continued things in one direction doesn't match up with the way you did it from another direction. And that's directly captured by the integrability of this tensor here, whether or not you can integrate things around the manifold and have things match up when you reach the other end, so to speak. So I better at least tell you, what does it mean for this tensor or for an almost complex manifold to have an integrable J so if you have that the Lie bracket of two holomorphic vector fields is always holomorphic, then that looks like a good start to your manifold being an actual complex manifold. And that's actually the notion of integrability here. So if you start flowing in the direction of a holomorphic vector field, and then you flow in another direction, then that's still the same as flowing in the direction of a holomorphic vector field. So you can extend things holomorphically by the exponential map. And it turns out whether a manifold is complex or not is related to the integrability of J and the vanishing of N, as we'll see. So I'll quote you now the result that characterizes complex manifolds. Okay, there's a remarkable theorem due to Newlander and Nierenberg. Okay, this result's been around for a while, 1957. We're going to write down a whole bunch of equivalent conditions for an almost complex manifold to be complex. So M is a complex manifold if and only if. Well, one of them we've seen, I've argued for. J is integrable, so the Lie bracket of any holomorphic vector fields is holomorphic. That means you can exponentiate out coordinates, holomorphic coordinates, and then continue your coordinate patches through your manifold. Another condition is that or this tensor n vanishes. If you like, this tensor n captures the defect from J being integrable. There's another condition that you could alternatively use, and that is that the exterior derivative is precisely equal to the sum of delta and delta bar, not a given on an almost complex manifold. Another one is, another equivalent condition is that delta bar squared is 0. Or the final one is that when you project onto the 2, 0 forms, the exterior derivative applied to 0, 1 forms, you also get 0. I'm not going to prove this. But you should, with this amount of background, be able to follow the proof, or at least be able to, with a minimum of looking things up, work out how to prove it. now I've built up enough formalism that we can finally talk about the things that I want to talk about, namely these Kähler manifolds. What are these things? So we have two nice structures, or three. We have symplectic manifolds. They're pretty nice. Hopefully you've enjoyed learning about symplectic manifolds in this course. We also have complex manifolds, which you've seen a whirlwind tour of. They're also pretty nice. And we also have Riemannian manifolds, which I haven't barely mentioned, but you've probably been exposed to several times in general relativity and so on. And we have, at the beginning of our discussion on complex manifolds, I introduced the idea of compatibility between these three kinds of structures on tangent space. Something being locally complex manifold, locally a symplectic manifold, and locally Riemannian. And it's kind of interesting to ask, well, what manifolds have all these three structures in such a way that they're compatible with each other? And the answer is a Kähler manifold. That's what you get when you demand that the manifold is a complex manifold which is compatible with being a symplectic manifold, which is directly related to it being a Riemannian manifold. These things turn up everywhere, especially in quantum mechanics, also in string theory. They're highly rigid things, very surprising properties. So here's the definition. When you can define these things in three ways, right? Depending on what you think is most fundamental. So in this course for us, it's natural to say that a Kähler manifold is a kind of symplectic manifold. So if you start with a symplectic manifold and pile on extra conditions, then you'll end up with a definition of a Kähler manifold. And here it is, right? You start with a symplectic manifold, and it's one of them with an almost complex structure that's compatible with it being a symplectic manifold. And also, that almost complex structure is integrable, meaning that it's actually a complex manifold as well. Now, if you loved complex manifolds, you'd define it differently. You'd say a Kähler manifold is a complex manifold where we have a compatible symplectic two-form. And if you really love Riemannian manifolds, then you'd say a Kähler manifold is a Riemannian manifold whose holonomy group is subgroup of UN, I believe. That definition I don't like so much, especially in the context of this course. But of course there are reasons why you might want to prefer that one. So that's the definition. Let's see where it carries us. Adding all these adjectives together will turn out to highly constrain the symplectic two-form omega. So what I'm going to do is track down all the consequences of these adjectives now on omega. Step by step, just impose adjective after adjective. So, using the fact that our manifold is a complex manifold, we can always write the symplectic 2 form in a local chart like so. There's some dz wedge dz's. There's some dz's wedge dz bars. And there's some dz bars wedge dz bars. Okay. So we've used the fact that the manifold is a complex manifold to express our 2 form in coordinates. Let's use the fact that our complex structure is compatible with the symplectic 2 forms. Well, that can only happen if you pull back omega and get omega. Well, that can only happen if the A's and the C's vanish. So what does this mean? Well, omega is a 1 + 1 form. Well, it's closed, right? We know that the 2 form omega is closed. It's like saying that d plus d bar is 0. I mean that C has to be 0, yes, thank you. Actually, I can upgrade that. Oh, I'll do it this way. Omega equals omega bar. What does that imply? That implies that went on before I write out that condition. Let's change our notation slightly. So the only coefficients that are left in this local expansion are the b's. Well, that's because we know what's going to come. Well, you'll see it as it happens. It's sort of useful to define h's to be I times by the b's. And in terms of these new variables, we have the following local expression. For omega. Okay, one or two more properties and then we've got everything we need together. Fourth property we can use, well, we know that omega equals omega bar. So that implies that hjk bar equals hkj. So hjk are the elements of a Hermitian matrix. Another consequence is that if you wedge omega n times, we know that it has to be non-zero. But that's actually the same as saying that the determinant over the complex numbers of the matrix H is not equal to 0. So H is a invertible Hermitian matrix. We've got one more property we haven't used, namely that because we have a compatible complex structure, that omega v comma jv is greater than 0, strictly greater than 0 for all v. So that means it's like a locally Riemannian. And that tells us, in turn, that as a matrix, H is positive. So H is actually a positive matrix. So to summarize, a Kähler manifold, the Kähler form omega in coordinates has the property that this matrix of coefficients here is a positive matrix. All right, how do we make Kähler manifolds? Let's find a recipe to come up with Kähler forms. Well, one recipe is fairly clear, right? If you have your favorite positive operator, stick it in the local form here. That defines a Kähler form. Actually, we can simplify things even a bit more. So a Kähler manifold is a complex manifold with a Kähler 2 form on it. How can we construct Kähler 2 forms? Well, here's a nice way. If you take a real valued function on your manifold and differentiate it enough times, you'll get something with the right number of components to give you a Kähler form. So if you get a real valued function on this complex manifold, and you look in some local chart and you form this matrix here, delta squared rho, dzj, dz bar k. It's like a Jacobian matrix, like a Hessian, sorry. Like a Hessian matrix, not exactly. And if this matrix here is positive in all charts and at all points on the manifold, then that is a nice function. We're going to give that function a name. We're going to call it strictly pluri-subharmonic. Strictly because there's strict inequality there. Subharmonic, well, harmonic's got to do with the Laplacian operator. A function is harmonic if it's a solution to Laplace's equation. It's subharmonic if it's a solution to Laplace's equation with a minus sign on the right-hand side, a minus constant. That Hessian there looks very much like something that would appear in a Laplacian. Pluri, well, it's got this particular form with respect to Z and Z bars. Now, if you can find a strictly pluri-subharmonic function, then you found a Kähler form, right? Because actually, just set h, j, k equal to this, and you have yourself a Kähler form. And then you have a Kähler manifold. Well, let's capture that. Okay, the proof's an exercise. So note, while delta squared is 0, delta bar squared is 0, delta bar plus delta bar delta is 0, delta bar is not 0. So that can work. There's actually a converse theorem. Says every Kähler form can be written locally in coordinates like delta bar of some function. Of some strictly pluri-subharmonic function. Didn't include that in my notes. Okay. So the function rho has a special name. It's called the Kähler potential, because this thing here looks like the coefficients in the Laplace operator, and something that's a solution to the Laplacian is called a potential, like the electrostatic potential. So why not call this a potential as well? It doesn't have the units of an electrostatic potential, but, well, the analogy is there. It's strong enough that it's worthwhile giving that name to it. Okay, that's long enough with abstract stuff. Let's look at a real example, or shall I say a complex example. I mean, the first comment is that there's loads of examples. There are very, very many Kähler manifolds. In fact, whenever you have a complex algebraic variety smooth, then you have a Kähler manifold. So they're easy to cook up. It's easy to build smooth complex algebraic varieties. You find a bunch of complex polynomials that vanish, and the set of points that they simultaneously vanish on is a complex algebraic variety, and that is by, I forget the name of the theorem, Kadeira embedding Chow. I can't remember exactly the name of the theorem, but that gives rise to a Kähler manifold. Loads and loads of examples. However, there's a couple which are directly relevant for quantum mechanics, which is the last thing we'll discuss. Simplest example is that of just the complex numbers themselves. It better be that this most familiar of examples is a Kähler manifold. So this takes a coordinate chart. Let's take real coordinates x1, y1, and so on. Complex coordinates z1, etc. And I'm going to write the most familiar two-form on this space that we now understand pretty well in this Kähler form. So complex coordinates are z1 equals zj equals xj plus I yj. Or root minus, yeah, been a bit inconsistent in this course, haven't I? So, well, as you see, I always avoid using i's on subscripts. That's a habit I picked up when I first learned quantum mechanics. It's really a bad idea to use i's on summations in quantum theory. Sooner or later you're going to run into this situation where you have I, or I subscript I, or something ridiculous like that. But mathematicians avoid this problem with the I and the subscript by choosing I as root minus 1 and refusing ever to write out I as the symbol I. I've done the worst of both worlds and taken I and root minus 1. But I've never, I don't think, knowingly ever wrote a summation sign with an I in the bottom. I hope it's been clear from the context. Now, we want to express our two-form omega, the one that we know and love for R2n, as d bar of rho. So we need a rho, right? Where are we going to get a rho from? A strictly pluri-subharmonic function. We need to find one of them. Well, they pretty much grow on trees. You know, it's pretty easy to make a random positive operator, and it's pretty easy to guess positive operators. And the most easy positive operator to guess is the identity, and that's the one that will lead to our form. So let rho be this function here, real part squared plus imaginary part squared, otherwise known as the sum of the absolute values, or just the absolute value of the vector of complex numbers. Is this strictly pluri-subharmonic? Well, if you take d squared rho dz dz bar, what do you get? We get the identity matrix, right? That's the world's simplest positive operator. And indeed, if you now use rho to write out, if you do take d bar of rho, let's see what we get. With an I over 2, well, in components we get delta jk, which are the components of a positive operator, namely the identity matrix. So this H matrix is the identity matrix. super. And our Kähler form, omega, is none other than the standard 2 form on the complex numbers. Fantastic. We have an example. And indeed, this is the example that we're going to focus on now when we express quantum mechanics itself as a classical theory. Now there's one more example that I'm not going to talk about because it's in the bonus exercise tomorrow. So the bonus exercise class doesn't count at all. It just gives you bonus marks if you want to do it. In the bonus exercise, you'll explore complex projective space, which is arguably, and you'll show that it's Kähler, I believe. I haven't looked at the exercise sheet yet. You'll show that, or you can add this to the exercise if you want, if it's not there. Complex projective space is another example of a Kähler manifold. It's the one that's arguably most correctly the configuration space of quantum mechanics. However, it turns out we can do everything we want to do just with this example, complex space, right here. So here's the final topic, quantum theory as a classical Hamiltonian system. Okay, I haven't gone crazy. Quantum mechanics is a classical theory, but it's a hugely non-local classical theory. So I won't be violating Bell's theorem in this course with a local hidden variable theory. I will not be doing that. It's not possible with the structure I'm going to tell you about, because what I'm going to show you is that quantum theory indeed can be regarded as a flow on a symplectic manifold, so really legitimately a classical theory, but it's a hugely non-local theory depending on local observables. So it's trivial that quantum mechanics is a non-local hidden variable theory. Just square the amplitudes. You have a non-local hidden variable theory. And I'm certainly not going to assert in this course that quantum theory is a local hidden variable theory. That's crazy talk. Instead, I'm going to highlight a structure that's maybe not apparent at first sight. All right, let's take M, our Kähler manifold, as just the complex numbers. And let's write out a ket in terms of a basis. And elements of this complex manifold, you can think of them as state vectors, if you want, I mean, if you're so inclined. Now what this is the configuration space for a qubit, an n-level quantum system. So a qubit is when n is 2, a qubit is when n is 3, and a qubit is when n is n. So this is like a spin n over 2 particle, just one spin n over 2 particle. The state vectors live inside that space there. Of course, to be a state vector, they have to be normalized. I'm not going to impose that constraint here. Subnormalized or supernormalized states are allowed. That's okay. Let's write down the Schrödinger equation now So let's suppose we have some Hamiltonian for our n-level system. So we have a Hamiltonian, some maybe very complicated spin Hamiltonian. And the Schrödinger equation, what does it tell us? Well, it says that the time evolution of our state vector must obey this first order equation of motion here. That's the Schrödinger equation. I've put a factor of a half in there for convenience. And in components, that tells us that the first derivative of zj coordinate is equal to the sum over sum over k of hjk times z, the k coordinate. So far everything maps kind of nicely between classical and quantum here. The points in this manifold are states. And if you thought of this as a classical phase space, then you'd also say the same thing. You'd also say the points in a classical phase space are the states of the classical system. So I'm going to draw a little cartoon of c to the n. This is c to the n. You think of this as a phase space for some classical system, and then you would say, well, each point is a state. And then you'd say, okay, if this is a classical system, what we need to do is introduce a function on this phase space, work out Hamilton's equations, integrate them, and that'll give us a flow. That'll tell us how the states change in time. And the remarkable thing, I find this totally astonishing, is that the flow generated by the Schrödinger equation, so this is also an equation satisfied by components, namely states, that turns out to be exactly the flow generated by a classical Hamilton function on this classical phase space here. So the proof is actually not even that difficult. So we're going to define ourselves a Hamilton function. Some function of j's and j bars on this. This is classical now. It's just a function. And what you do is you take those matrix of coefficients h, j, k that you use to write out your Hamilton operator in terms of these ket bars, and you build this quadratic form here. It's just a function on our phase space. And now, well, it's a function. We know what to do, right? When you have a function on a symplectic manifold, how do you work out the flow? Well, first you compute d of h. Well, that was a Leibniz rule away. And then you want to work out the vector field generating the flow on our phase space. And the way to do that is you take your symplectic 2 form, which we know what it is. and you find that vector field that when you put it into omega via the interior product, you get d of h. And, well, okay. It's 2 or 3 lines of computation. I'll just give you the answer. And that's what you get. You get this vector field popping out from that particular Hamilton function. Let's look at the flow of this vector field. You can get that by exponentiating the vector field. If you have some function and you want to see how it changes under this flow, then we know it has to obey this equation of motion. And what we're going to do now is just choose. So f depends on t here. So let's just choose f at time 0 just to be the jth coordinate, the jth complex coordinate. Then this equation here, what does it tell us? That the coordinate after some time t, well, xh, the change in the coordinate at some time t is x of h applied to that. But then if we take a look at our vector field over here, we see that the second term drops out, right? This is the anti-holomorphic bit. Here's the holomorphic bit. And we're left with this equation. Which is none other than the Schrödinger equation with a minus sign. All right, so I should have taken for this function up here a minus. I just realized. Minus.
Isn't it fine with a minus? Because it's on the other side?
Oh, yeah, it's fine with a minus. Yeah, sorry. Thank you. It's actually fine with a minus sign. Because the Schrödinger equation is the I on the other side, yeah. awesome. So we've just learned that the Schrödinger equation, which is introduced in a somewhat ad hoc manner sometimes in some courses, can be really thought of as a classical flow on a classical symplectic manifold, as the equation of motion governing the flow on a symplectic manifold. Now this idea, this is just sort of the kernel of the idea. You can push this very far indeed. So the words that I'll leave you with, you might wonder, oh, okay, I've done this for this nice flat complex numbers. What happens if I have a complex manifold, a more curvy one? Then what do I learn? Do I learn, is this somehow a nonlinear version of quantum mechanics, or what do I learn? Well, actually, this is current research. Right? You can apply this to other manifolds to other Kähler manifolds, and you will get nonlinear generalizations of quantum mechanics. To my knowledge, there's only a few papers that actually explore this, and I wouldn't call it completely dead as a theory, as a field. So there's some merit to thinking along these lines. Another thing you can do with this is you can take the complex numbers and look at subsets of the complex numbers and think of these as variational manifolds. So you're no longer allowing all possible states, but you're allowing some subset of states, some variational class. And you can look at the dynamics generated by the Schrödinger equation that stays as best as possible within a variational class. That leads to something called the time-dependent variational principle, which is an extremely powerful technique to solve many-body systems. So it's another topic you can go into from here. But this, I think, is the best moment to finish up the course. Thank you very much for joining me on this journey through the theory of symplectic manifolds and complex manifolds. And I will see you next semester, I hope. Thank you.